CPU stands for Central Processing Unit. The CPU is the primary component of a computer that performs most of the processing required to execute instructions from programs and the operating system. Often referred to as the brain of the computer, the CPU interprets and executes instructions from software, manages tasks, and performs calculations essential for the system's functionality. Let's review key components of a CPU. First, the control unit, CU, directs and coordinates the operations of the CPU and other components of the computer. The control unit fetches instructions from memory, decodes them, and decides which internal components, like the ALU for calculations, should execute tasks, and manages communication with external devices through I/O input-output operations. The CU control unit acts as a traffic controller for data flow inside the CPU. Next, the ALU, Arithmetic Logic Unit, performs mathematical operations like addition and subtraction, and logical operations like comparisons of greater than or equal to. If a program calculates 2 plus 3, the ALU performs the calculation. Registers are another key component of a CPU. These are small, high-speed storage locations inside the CPU used to temporarily hold data, instructions, or addresses during execution. A register might hold the result of a calculation before storing it in memory. The cache is another key component of the CPU. The cache is a small, fast memory located inside or near the CPU, storing frequently used data and instructions to speed up processing. If the CPU repeatedly accesses the same variable, it's stored in the cache to avoid fetching it from slower main memory. And the clock is another key component of a CPU. The CPU's operations are synchronized by an internal clock. The clock speed, measured in hertz, you'll see it as Hz, determines how many instructions the CPU can process per second. A CPU with a clock speed of 3 GHz can theoretically perform 3 billion cycles per second. You'll hear of clocking in gaming a lot of times as they're trying to improve their gaming performance by overclocking a computer. The CPU works by fetching. The CPU retrieves an instruction from memory, RAM, random access memory, based on the program counter, PC, which keeps track of the next instruction to execute. Fetch the instruction to add 2 numbers from memory is an example. The CPU also decodes. The CPU decodes the fetched instruction into a form it can understand, determining what action to perform. For example, the instruction add R1 and R2 tells the CPU to add the values stored in registers R1 and R2. Next, it works by executing. The CPU performs the operation specified by the instruction using its ALU or other components. For example, the ALU adds the 2 numbers in R1 and R2 and stores the result in another register. And store. The result of the operation is written back to a register, memory, or storage device as needed. So the CPU will store, for example, by saving the results of 2 plus 3 in main memory. This cycle, known as the fetch, decode, execute cycle, repeats continuously while the CPU is running. There are various types of CPUs. You have the single-core CPU, which processes instructions one at a time. Early CPUs were single-core, limiting multitasking capabilities. The Intel premium processors from the 1990s are examples of that. Next, we have multi-core CPUs. These contain multiple cores, each capable of executing instructions independently, and this improves multitasking and performance for modern applications. You may have heard of a quad-core CPU that can run 4 tasks simultaneously, and the ARM CPU. This is a type of processor designed with a focus on energy efficiency, commonly found in smartphones and embedded devices. CPUs in most Android devices and Apple's A-series chips have ARM CPUs. And the x86 CPU is a widely used CPU architecture in desktops, laptops, and servers designed for high performance. Intel Core i7 or AMD Ryzen processors are examples of x86 CPUs. The CPU helps to execute programs. The CPU processes every instruction from software applications, enabling them to function. When you open a browser, the CPU executes instructions to render the web page. The CPU provides multitasking, as modern CPUs with multiple cores and threads allow simultaneous execution of multiple tasks, such as running a video call while browsing the internet. And the CPU provides hardware coordination, as the CPU interacts with
other hardware components
like memory, storage, and GPU
to ensure smooth operation.
The CPU sends instructions to the GPU
to render images on the screen.
For example, there are performance metrics for the CPU.
We mentioned clock speed,
measured in gigahertz, GHz.
It indicates the number of cycles the CPU can perform per second.
Higher clock speeds often translate to faster performance for individual tasks. And there's the core count. The number of cores determines how many tasks the CPU can handle concurrently. More cores are better for multitasking and parallel workloads. And the threads. Threads are virtual cores created using hyperthreading
or similar technologies,
allowing each core to handle 2 tasks simultaneously. Then you have cache size. Larger caches reduce the need to fetch data from slower main memory,
improving performance.
And ISA, instruction set architecture, which determines the type of instructions the CPU can execute, like x86 or ARM. When you open a spreadsheet, for example, the CPU fetches the program's instructions from memory. It decodes and executes the instructions to draw the interface, display data, and respond to your input, like updating totals when you modify numbers. The CPU coordinates with the GPU to render the screen and storage device to save your changes. The CPU is central to the operation of any modern computing device, playing a critical role in executing software, managing hardware interactions, and enabling multitasking. Its speed, efficiency, and architecture significantly affect the overall performance of a system.